is a function or not, we use what's called the vertical line test. Vertical line test says you place your pencil, a ruler, the side of your calculator, anything that's vertical. You place it on the left side of the graph and you're going to slowly move it across the graph. And what you're looking for is, does the graph, not the axes, but the actual graph, cut that vertical line more than once? Okay, so let's look at the line. I'm going to start on the very left-hand side. How many times does the graph, not the axes, the graph cut through that vertical line? So you can use a pen, you can use your finger, you can use a ruler, anything that's vertical. How many times does that line cut through that pen? Once. And if I move it a little bit further along? Once. And if I move it a little bit further along? Once. And it doesn't matter where I go, it's only ever going to cut through once. That means yes, it is a function. Because what that means is we don't have an x value that's got two different y values. So if it only cuts through once, yes, this is a function. Okay, so we don't normally do this, but let's just draw some vertical lines just to show what we mean. And I'm not putting them in any particular spot. And again, you're not looking at the axes, you're just looking at the actual dark line itself. Cuts through once, 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 once. If the answer is always once, yes, it is a function. So some people can just eyeball it. Some people need to put their pen. Sometimes the pen is too thick. Some people like the edge of a ruler. Whatever works for you. Very left-hand side. Uh-oh. What happens right away? Cuts through twice. Okay, well, what if I move it over? Still twice, still twice. If it ever cuts through more than once, what's the conclusion? Not a function. This guy you'll meet in grade 12, his name is a cubic. He's a pretty cool function. And so if I look here, and again, you don't have to draw the lines. I'm just showing for the visual people what's going on. How many times does that line cut through? Once, and here. Once, and here, once, here, once. Doesn't matter where I put the vertical line. If I move it from left to right, what happens? It's only going to cut once. Conclusion? Yes, it's a function. Well, what if the graph isn't a nice curvy line like that? What if it's just a set of points? And a graph that has a set of points is called a scatter plot, because it kind of looks like the points are just scattered all over the place. What you're looking for is two or more points on the same vertical line. So we're really going to do the vertical line test. We're just looking at the dots themselves. So if I come to the first dot, is there any other dot that's on that same vertical line? No. What about the next dot? No. Third dot? No. If I go to any dot, is it going to hit any other dot vertically? No. What does that tell you? Yes, it is a function. Okay, if we look at the second one, here's the first dot. Does it hit any other dot? No. Uh-oh. What do you see here? So I'm just going to draw the line for that one to show the difference. There's another spot it hits 2 points. There's a third spot it hits 2 points. Doesn't matter how many times. If it ever hits 2 points, the conclusion is not a function. That's the first skill for today. You need to be able to look at a graph, whether it's a line, a curve, a set of points, and decide function or not a function. It's called the vertical line test. Here's just some things you need to know about graphs. Sometimes the data points are joined to form lines and curves. Sometimes they're left as individual points. And so here's two examples. We've actually looked at both these graphs before. This is from a couple days ago, maybe yesterday. This one is the same one as above. Why? Why do sometimes as mathematicians we like to join those points and get nice curves or lines, and why do sometimes we leave them alone? Anyone have any thoughts on that? Lexi?
Because it's one thing and then the shoe size is different.
I like that you just need to explain that a little bit better. So it's one thing and then it's different.
Like, everyone has different shoe sizes, so they're not going to join them all together.
You're definitely on the right path there.
It's not a measure of time.
It's not a measure of time. Doesn't have to be time, though. That's a good thought because there's definitely time going on. Cody?
For that first one,
Ooh, I like that idea. Let's go with that. Who can expound on that a little bit? So if we look at this one, for example, and we know this is time from yesterday, could we have 21 minutes? Could we have 22 minutes? Could we have 21 and a half minutes? So could we add seconds to it? So there can be values every single where in between. What do we measure shoe size in? Full size and half size. That's it. Can we have quarter? Could we have thirds? Could we have 3/4? So you don't need to know these terms until grade 12, but I'm going to tell you now. This is called continuous data. Continuous data. And the other one's called discrete data. And if you go to university and you go into maths and sciences, there are specific courses, one that just deals with continuous data and one that just deals with discrete data, because they're very different things to scientists. So why? Sometimes the values can be between the x values. Sometimes the values can be between the x values. And sometimes that's impossible. Sometimes the values can be between the x values, and sometimes that's impossible. So an example of impossible would be shoe size. Okay? We don't have a 6.1. We don't have a 9.2. Okay? We got full sizes and half sizes, that's it. So the second skill you have to be able to do today is to look at a situation, look at a graph, and decide, does it make sense to join the points or would we not join the points? So when do we join, when do we not join? The second thing you need to know about graphs is when you have curves or lines, sometimes there's a dot at the end and sometimes there's nothing. And so if you look at this one here, the right-hand side has a dot, left-hand side has nothing. You can't see what I highlighted there. There we go. So when you have a curve or lines, sometimes at the end there's nothing, sometimes there's a dot. Mathematically, that means a huge difference between the two. The dot means that this graph stops. It means that the largest x value would be 3, and the highest y value on the right-hand side would be 8. There's nothing past 3. It doesn't continue. What's going on the left? So when it just kind of trails off the graph there and there's no dot. Keeps going. Now mathematically we would draw an arrow, but computers have a really hard time putting arrows on graphs, so what they'll do is just trail off like that. What that means is that it keeps going. Keeps going to what? Infinity. So if you're to draw a graph, you're going to put an arrow on the end. You just need to be aware that textbooks and computers have a hard time printing that. So when they want it to stop, it'll be a really clear stopping point. If it just kind of ends where the graph ends, what that means is it goes on forever and ever and ever. Why? So why does sometimes it stop and sometimes it keeps going on forever and ever and ever? Ooh, I like that, more specific. Other ideas? So let's talk about shoe size. Would we graph shoe size to infinity, or is there a stopping point for shoe size? What's the largest shoe size that they make? I've heard of 20s for basketball players. I've never heard bigger than 20. Who, sorry? 28, that's crazy. I could put both my feet in a 28. That would be crazy. What's the smallest shoe size that they make? 4s are the smallest. And I only know that because my mom wears a 4. It's like little baby slippers. It's ridiculous. So those would have stopping points if we were to graph. We're not going to graph negative shoe size. That doesn't make sense. We're not going to graph shoe size into the hundreds because that doesn't make sense. What about riding the Ferris wheel, for example, that we looked at yesterday? Could we, in theory, ride it forever? If we had food and if we had everything else, in theory we could. There's not necessarily a clear stopping point. It's not like when the ride hits 3 minutes exactly that it just stops dead. Operators choose that. So it really, again, just depends on the situation. So some situations have clear endpoints. Some situations have clear endpoints, for example, shoe size. Others go on forever. Others go on forever. An example is usually things that involve time. It'd be nice sometimes if we can stop time and just take a break, but that doesn't happen in the real world. Christopher, is that a mature use of my ruler? Could you put it down? So let's go back to this idea of domain and range. Who has got a good memory and can remember what the definitions were from 3 days ago? Domain is X and range is Y. And how do you remember which is which? Alphabetical. Did Right Brains, did you figure out a way that works for you guys? Sorry? You just remember it willy-nilly. Yeah, it doesn't work for left brains. Okay, so when we rate domain and range of the graph, we're going to start with domain. And domain is all the X values. So what we're going to do is we're going to look to the left and we're going to look to the right. When we do range in a second, we're going to look up and down. So when you look at domain and you go to the left, you need to say to yourself, what is the smallest possible X value that I can have? So if I start at -1, which is the first on the left, is there graph there? Does the graph pass through -1? Does it pass through -2? Does it pass through -3? Now, even though the graph has ended, would there be a value at -4? What do we know about this part that just kind of trails off? Well, we talked above that it's got an arrow. So if we had space to keep drawing it, would there be a value at -4? Would there be a value at -5? Would there be a value at -10? Would there be a value at -100? So what do we say the smallest possible graph for this, or possible value for this graph would be? So what's the smallest possible negative value? Negative infinity. That would be the smallest possible X value for this graph. Okay, let's do the right-hand side of the graph. So the first value is 1. Is there graph at 1? Is there graph at 2? Is there graph at 3? Is there graph at 4? So what's the largest possible X value? You're not going to turn. I'm going to turn and show you the questions, but we need to look at the graph. We're going to do the same thing. You can't see that. We're going to do the same thing with the ranges, just we're going to look down and we're going to look up. Okay, so you stay on the graph because we need to look at it. Switching colors. Now we're going to look down and we're going to look up. What is the smallest possible Y value? So we'll start at 0 and we'll go down. Is there graph at -1? Is there graph at -2? No, there's nothing happening at -2. Where does the graph bottom out? What's the lowest possible, value? -1. Okay, let's do the positive. Is there graph at 1? Yeah, there's actually 2 spots if there's graph at 1, and that's okay. Is there graph at 2? Is there graph at 3? Okay, let's jump up. Is there graph at 6? Is there still graph at 8? What about above 8? Well, there isn't on the right, but is there on the left? So there would still be graph at 9. What about graph at 10? So because this side goes on forever, what's the highest possible value? Infinity. So I want to just correct this because this was supposed to be Y's, not X's, so let's just fix that. So we said if we look down, the lowest value we saw was -1. The highest value we saw was infinity. No, as long as the other one keeps going, keeps going. Now we're going to look at two different ways to write domain and range. You need to be able to recognize both in a multiple choice question, but you can pick whichever one you like better. At the beginning, doing domain and range is going to make your brain hurt. You're going to be like, what? What is this notation? What is going on? The more we work with it, the easier it's going to become. And if you continue on in pre-cal, you're going to see domain and range a million times between now and graduation. Functions and domain and range are the key of the next 2.5 years. So at the beginning, if you're, that's okay. By the end of this unit, we want you more here. Let's do what's called interval notation first. Interval notation says we give the lowest and we give the highest, and we're going to put special kind of brackets, which I'll talk about in a second. I'm going to use a D for domain and a range for R because I'm too lazy to write out the whole word. So now whenever you see D and R, it's always going to mean domain and range. We start with the lowest value, which we said was, no, I can't even remember, negative infinity. And I'm going to put a comma. That's a terrible infinity. I need to redraw that. Left brain can't help it. And the highest number we said was 3. I'm going to put a round bracket in front of the infinity, and I'm going to put a square bracket around the 3. Round brackets mean that number is not included. Square brackets mean the number is included. The reason we use a round bracket around negative infinity is because negative infinity is not really a number. It's really just an idea, because you can take infinity and then you can add 1. And that's really confusing. If infinity is the biggest and you can always add 1 to it, what does that mean? All you need to know at this point is if there's an infinity or negative infinity, you're going to use a round bracket. We're using a 3 because the graph actually passes through 3. There is a black dot at 3. That's a clear part, so we call that a square bracket. If there had been a white dot at the 3, we would have used a round bracket. Confused yet? Okay. Off to the side, red pen. Infinities or negative infinities are always going to be round brackets. If the graph has a black dot, so a clear black dot, those are always going to be square brackets. If the graph had a white dot, or what we call an open dot, those would be round brackets. And this is going to become more clear as we do a couple more questions, so don't panic yet if you're not understanding this. The range, the lowest value we said was -1. The highest value we said was infinity. Did the graph actually pass through -1? Look if you're not sure. Did it actually pass through -1? Was there actually a dot there? Maybe not that you can see, but is there a little tiny dot on the graph? Yes. So if that has a dot, meaning the graph passed through it, I'm going to use a square bracket. Infinity, I'm going to use a round bracket. These are symbols, and remember, to a mathematician, symbols are words. What you're saying without using all the words is all the possible y values are from -1, including -1, all the way to infinity. That's what this is saying. This is saying all the possible x values are all the way from -infinity up to 3, including 3. It's notation without having to use all those words. That's called interval notation. I'm going to give you the exact same information, but I'm going to use a different notation, which is called set notation. Why 2 notations? Because the math world can't decide which one they like better. One is more popular in North America and Asia, the other is more popular in Europe, and they can't figure it out. So because we don't know who's going to be teaching you when you go on to university or post-secondary education, or where you're going to end up, we're teaching you both. You have to be able to recognize both, but you can pick whichever one you want to actually give the answer. Set notation says this, is I need to say all the numbers from -infinity to 3. So I'm going to start with x, and I'm going to say less than 3. Why is that the same thing? Well, what kind of numbers are less than 3? Give me an example of a number that's less than 3. 2, give me another one. 1, give me another one. -1, give me another one. -2. And how long could we keep playing this really fun game? Forever, because all the numbers less than 3 are all the way up to -infinity. It's just saying the exact same information, it's just 2 different ways to say it. Here I want to go from -1 all the way up to infinity. So that means that y is greater than or equal to -1. Why did I use an x here and why did I use a y here? Why did I suddenly change that up? because domain is about x and range is about y. Well, what kind of numbers are greater than negative 1? 1, 2, 3, 10, 100, 1,000,000. How long could we keep spitting out numbers? Forever. These say the exact same thing mathematically. How are we feeling so far? You're probably here, and that is A-okay at this point. It's actually funny because, like I said, the mathematicians can't decide which one we like better. Usually in classes like this, it's split 50-50. Half will end up loving interval, hating set. Half will love set and end up hating interval. Okay, that's all we're going to do for the rest of the day is just practice domain and range. Do we need paper? No, we'll do it without paper. We'll squish it on this side. So first thing, let's talk about what the graph means. What does it mean on this left-hand side when it comes right to the edge and just kind of trails off there? So I like to put the arrow so that it's really clear in my mind that that's going on forever and ever and ever. What does it mean on this side when there's a really clear dot? It stops. That's the last point on the right-hand side. Do you see the difference between when it stops and when it keeps going? Visual people, grab your ruler because this makes domain and range easier if you're visual. I'm going to put it along the x-axis, and that's what we want to look at are the x values. So I want to look at the left-hand side first because I want the smallest x, and then I'm going to look at the right-hand side. So I'm going to start at 0, and I'm going to go towards the left. At negative 1, am I hitting graph? Negative 2, am I hitting graph? Negative 3, is there still graph there? Negative 4, negative 5, negative 6. I'm out of room, but if I keep going, would there still be graph? So what is the lowest possible x value? Negative infinity. I'm just going to write that on the left-hand side, and we'll come back to him in a second. Why negative infinity? Because there's an arrow, and the arrow means it goes on forever. I'm going to go back to 0. This time I'm going to push the ruler on the right. At 1, do I hit graph? At 2, 3, 4, 5, 6. No. So what was the lowest, or the highest, sorry, possible x value? I'm going to write that on the right, and we'll come back to him. If the ruler thing does nothing for you, then don't worry about it. It's just a visual way to look at it. Now I'm going to do range, and I need to look down, and I need to look up. So first it was left and right, now it's down and up. Okay, so I'm going to put my ruler vertically at 0, and I'm going to work down. Is there graph at negative 1? Yeah, 2 spots it hits graph, and that's okay. Negative 2. Negative 3. Negative 4. Well, there isn't on the right. My pen's in your way. But is there on this side? Yeah, and that's okay. What about negative 5? I'm out of room, but what does this arrow mean? We can keep going. So the lowest possible y value is negative infinity. Back to 0, and this time I'm going to go up. Is there graph at 1? Is there graph at 2? Is there graph at 3? That's where I run out of graph, so the highest possible value is 2. I'm going to start with interval, then I'll give you set, and I'll give you both every single time. You can pick and choose which one you like better. Domain is the smallest to the largest, so the smallest is negative infinity, the highest is 5. All I need to do is pick the brackets. If it's infinity, it's going to be a round bracket. If there's a number and it's a clear black dot, it's going to be a square bracket. Mathematically, that's saying all of the numbers between negative infinity and 5. Every single value from negative infinity all the way up to 5 and not beyond. I'm going to do the same interval notation for range. Range, the lowest we said was negative infinity. The highest we said was 2. Negative infinity gets a round bracket. 2 has a dot there, but gets a square bracket. Now I'm going to give the exact same thing in set notation. What you need to say is all the numbers that are to the left of 5. How do we express numbers that are to the left of something? That's less than, because left is smaller. So we're going to say x is less than or equal to 5. Mathematically, that says all the values to the left of 5, which means every single number from 5 all the way to negative infinity. Here I need to say all the numbers from 2 to negative infinity. So how do I say down or below? What kind of numbers are below 2? Are they less than 2 or greater than 2? Less than 2. So y is less than or equal to 2. You can pick, but you can't mix and match. If you use interval notation for domain, you can't use set notation for range. They come together. Okay? Pick and choose, doesn't matter, but you need to be able to recognize both. Show me your thumb, and if we're here, that is A-okay at this point. You have to put it high. I can't see when it's in front of you. Good. Okay, let's look at B. Left, right, then up, down. I'm going to go to the left first. Is there graph at -1? Is there graph at -2? Is there graph at -3? Is there graph after -3? So what does that tell you? What's the lowest possible x value? -3. And you don't need to write it on the graph. I just do so that I remember it, so when I come back to do the two domains. Okay, now I'm going to push towards the left, or sorry, towards the right. Is there graph at 1, 2, 3, 4, 5, 6. Okay, so the highest x value is 5. Range, you look up and down. There's not even graph at 0, not at 1, not at 2. What's the lowest y value? Where does the graph start? 3. Okay, just show you there. There's graph at 3. Is there graph at 4, 5, 6, 7, 8? Ooh, no. So what's the highest possible y value? 7. What do D and R stand for? Domain and range. Domain is X, range is Y. You are going to say those words 500 times between now and graduation. Again, I'll give you both. You pick and choose which one you like better. I'm going to start with interval notation. The lowest possible x value we said was -3. The highest we said was 5. Is there a black dot at -3? Yes, that means it gets a square bracket. Is there a black dot at 5? Square bracket. You don't need to know this, but the reason the math world is split on this is this was the original way domain and range have been done for hundreds and hundreds and hundreds of years. The problem, let's imagine these weren't black dots. Let's imagine they were white dots. What kind of bracket would this get? Round. And this would get round. And if I just give you this as notation, what does it look like? It looks like a coordinate point. And that's why the math world's like, that's kind of confusing because this all has to do with graphing. And so if I just give that, is that a point? Is it a domain? What's going on? That's why we're kind of going towards the other notation. But the math world is funny, and when we've done things for hundreds of years, they're like, no, we're not changing. So that's why there's kind of two notations right now. Okay, I'll go to range, do the same notation. Smallest number was 3. Highest number was 7. Is there a dot at 3? Yes, there is. Is there a dot at 7? Yes, there is. Do you have one you like better? Oh, but like this is going to take, the math world is not fast. So it's going to take hundreds of years before they fight it out. Right? If you look at the history of math, there's a whole poster. Yeah, that's 3,000. No, it's even more. That's 6,000 years of history right there on that one piece of paper. We are not a fast world. We do not make fast decisions. And it's funny because I teach IB teachers how to teach in the States. They're like, well, that's stupid. Why can't they do it our way? I'm like, well, Europe invented it, so they kind of get to do it whatever way they want. But it's really North America. It's like, no, we want our way. Well, it's been around for thousands of years. Why do we get to pick? Give you the other notation. How do you say numbers? Oh, well, this isn't less than or greater than. We've already talked. How do you say between mathematically? You've forgotten. Grab your red pen. This came up in grade 9. It'll come up again in grade 11. To say between, we use less than or equal to x, less than or equal to, or a y if it's range. It just matters. So it's a less than, a variable, less than. Those three symbols put together is the English word between. So because this doesn't have an infinity, what I need to say is between -3 and 5. So I start with the -3. I say between and I put the 5. That means mathematically between -3 and 5. This one isn't also between because I don't have infinity anywhere, so I'm going to say 3 is between 7. And this is why the math world is split, because yeah, the brackets are confusing if they're round, but whoa, what the heck is that? Right? That's why there's all this, what's going on? This should be a Y. Sorry, my fault. It should be a Y, because it's range. Was that what you were going to ask me?
Yeah.
Let's look at this crazy graph. This one you'll meet in grade 11. He's called a parabola. He's pretty exciting, actually. We do 3 units on him in grade 11. What does it mean up here when the graph just kind of trails off? Okay, so I like to put those arrows just so it's really clear in our mind it's going on forever and ever and ever. Left and right first for domain, we look to the left. So is their graph at -1? Yes. -2? Yes. -3? Yes. -4? And even though I've run out, what does this arrow mean? It's going to keep going on forever and ever and ever. So if I had a huge piece of paper, would there be graph at -4, -5, -6, etc., etc.? So what is the lowest possible x value? -infinity. And let's go on the right-hand side. There's graph at 1, there's graph at 2, there's graph at 2.5, there's graph at 3. What does this arrow mean? On forever and ever and ever, the highest value is going to be infinity. Why? Because there's an arrow on the left and an arrow on the right. And when there's arrows on left and right, it's always going to be -infinity and infinity. The range, we're going to look down, then we're going to look up. Is their graph at -1? Yes. -2, -2.5. Yes. Uh-oh. Where do we run out of graph? 4. We can agree it's -4? We're estimating that, and that's okay. Okay, let's look up. Is there graph at 1? Yep, 2 spots. Graph at 2.5? Yep, 2 spots. Graph at 5? Yep. What do these arrows mean? Keep going, so the highest is going to be infinity. How are we doing so far? Because that's the first step, is to get those 4 values. If you can't get those 4 values, you can't get the notation. Domain, smallest value we said was -infinity. Highest value is infinity. What kind of brackets? Round if it's -infinity, and round if it's infinity. And again, I know it looks weird, but that's notation. What you're saying to the person is it is every single value from -infinity to infinity. It's just not using words. Okay, let's do the range, then we'll come back. What's the lowest value? -4. Highest value? Infinity. What kind of bracket does -4 get? Square. What kind of bracket does infinity get? Round.
Should like the one we did for domain, should there just be a sign that means added number?
That's what's coming in the other notation. Okay, well, what did we do before when we had infinities? Well, that's when we use the less than and greater than. The problem is they are both infinity. So how are we going to say all of the numbers between -infinity and infinity? Go back to the last unit for a second. Remember the number families we did with the stacking bowls? What was the very top bowl, the smallest bowl? Naturals. And naturals fed into the wholes. And wholes fed into the integers. Integers split in there was those 2 groups. There was the rationals and the irrationals. We took all that. And what was the major family at the bottom? The reals. That's what this is. This is notation for the reals. What are all the numbers between -infinity and infinity? The real numbers. So here's the notation for set theory. Are you ready? X. Then I'm about to use a Greek symbol, so I'm going to say E, because we call it English E, but watch how I write it. Brah, come on. You're in grade 11. Is that mature? You should be an example for everyone else in this room. Put the ruler down. So I'm going to start with what looks like a C, and then I'm going to put that middle line for an E. It has to look like that because that's a Greek letter, and I'm going to tell you in a second what it means. And then what's the notation we use for the reals? What was the letter? It was R. What the heck is that? Well, we read that as XER. That's how we say it. What it means is X is an element of the real numbers. X is an element of the real numbers. What does that mean? X is an element of the real numbers. Well, it's a fancy way of saying X is a real number. And what does it mean if X is a real number? It's every number from negative infinity to infinity. Those are your two choices. You're either going to use the first one, which is interval, or the bottom one, which is set. Whew, questions so far. Let's just add what the heck is this. Anyone know what Greek letter it is? We call it E in English, but in the Greek alphabet it's called epsilon, which you probably heard of in movies because there's always fraternities that have epsilon in them. So it's epsilon. Why is it Greek? Because the Greeks came up with this notation. What it means is an element of. They chose E for element. What does that mean? That's a fancy way of saying belongs to the real numbers. You are going to see XER between now and graduation probably 5,000 times. XER, XER, just put that in your head. You're going to see it over and over. We're just introducing you to it now. It's going to come back in grade 11 and back in grade 12. Whew, okay, I have a number and I have infinity. That always makes us happy because there's no XER in this one. How do I say all the numbers that are bigger than negative 4? Y is greater than or equal to negative 4. Whew, how are we doing so far? Okay, let's do the line. What does it mean when the ends are just really kind of, they're right at the end, and we don't know, lines, arrows. Going to the left first, negative 1-ish is their graph. Negative 2.5, negative 5. Well, there's no graph down here at negative 5. What are you talking about? Yeah, well, we could continue this line, and because of this arrow, what's going to happen here?
Oh, it's going to get there.
It's going to go all the way to negative infinity. So, oh, you're already ahead of me, yes. What's happening over here on the right-hand side? Well, there's graph at 1, there's graph at 2, there's graph at 2.5. Well, again, I don't see graph at 5, but if I kept drawing it, it would get to infinity. Andrew, wake up. Range, we're going to look down, and then we're going to look up. Is the graph at negative 1? Graph at negative 2.5? Graph at negative 5? Well, this doesn't stop. The arrow keeps going. So what's the lowest possible value on the y-axis? Negative infinity. The highest arrow up here means infinity. Domain, range. Interval first. Lowest we said was negative infinity. Highest we said was infinity. Brackets. And now please note, we call them round and square, but remember these actually aren't brackets. What are they? Parentheses. So there's actually parentheses and brackets. We just call them all brackets. Okay, range, negative infinity to infinity again. I'm running out of room there because of the hole. What kind of bracket? Round and? Set notation. What matches when there's two infinities? What's the same thing as negative infinity to infinity? X, E, R. Make sure it's an E like that. It's not an E like this. It's not an E like that. It's not any other kind of E because it's a Greek letter. It's not an English E. Well, what about over here? Y-E-R. I'm going to make the strong suggestion, because you're going to help yourself out for grade 11, is that for all of these you give the two notations. Even if you already have a preference to one you like better, it's really good to practice giving both. But it's up to you. You only have to give it in one way. Well, what if it's a scatter plot and there's not all those arrows and lines and crap and everything else? Then what do we do? Well, I actually already showed you this when we did the definition of domain and range. All we do is just list out the values. So the domain, what's the smallest possible x value? Well, where's the first point? Ooh, if this is 6 and this is halfway, this would be 3. And where's the next point? And where's the next point? And where's the next point? Do you see a pattern happening here? So what did we do? We just listed them out. That's all. If there's not those lines and those arrows, you just list them out. What about range? So what's the smallest y value now? So now we're looking at the y-axis. 5. Well, is this one right at 10? Yeah, 12, 11-ish. Can we concede? Can we concede on 12? Okay, this one. 16. 18, 17. What do you want to do? This one? Drew? Okay, if you're tired, you need to go. Okay. This one, did we already have him, or is he a different value? Yeah, we already have him. This one? He looks a little bit lower. 11. And the very last one. And do we? No, we don't already have 6. Then we get to something like this, and we're like, why? Why can't it just be with arrows? Okay. Well, Yeah, that's it. We leave it. That's it. Domain and range. Okay, so the first dot. No brackets, not with points. Just leave it. Eight, can we convert? I'd 157 too, I'd be okay. The next one, there's 2 of them, and that's okay. 160. 162, 3, 2. Then 165. And we just need to write it once. Ooh, you can't see the end. Are we happy with those values? A few of them we estimated, and that's okay. Okay, now the range, so what's the lowest value? We're looking now at the y-axis. 44. Someone said nope to that one. 44 looks a little bit low to me, because halfway here would be 50. I was going to go 6, but I can go 8. I'm okay with that too. Ooh, I think we got another one in here, a couple more in here. 60, 53. We got one close to 60. 59. Do we have exactly at 60? Yeah, there's 2. That's okay. 62. I could go 63 as well, so we're just estimating. Got 2 more, I think, here. Yeah, so if this is 70, yeah, maybe 63. And then one right at 70. Let's just review everything that we've done today. Very first thing is you need to be able to look at a graph, whether it's a line, a curve, or a set of points, and you need to decide if it's a function, yes or no. Turn to someone in front, behind, beside you. Tell them, how do you know if a graph is a function? Okay, face back. Remember, phone should be away right now. The second thing we talked about is whether a graph has points or whether it has lines and curves. What kind of graphs have points and what kind have lines and curves? Turn and talk. Whoever didn't just talk is now going to talk. Okay, face back. I'm so not done, and people are packing up. People are putting stuff away. What is going on? I am not done. How do you know whether a graph is a function? Tim. More specific, what kind of line? Vertical line, right? It has to be vertical. If it goes through more than once, it is not a function. When are graph dots and when are they lines or curves? Oh, now it gets all quiet. Look at that. If it makes sense to have the values that are between. Okay, if it makes sense to have the values in between, they are curves or lines. If it doesn't, they are dots. Last thing, and really this was setting us up, was all about domain and range. What is a domain? Turn and tell your partner the definition of domain. Respond back with the definition of range. You need to know how to do it for graphs, whether they're continuous or whether they're discrete. Again, I'm going to suggest at this point that you give both the notations until you're familiar with it. If you really like one, that's fine, but just be aware you need to be able to recognize the other. Homework for the weekend, 294.